How do you determine the typical value when you're staring at a massive data set? Like, let's say an endless spreadsheet of 1,000 house prices.
Right.
And how do you measure exactly how spread out those data points actually are?
Hmm.
And crucially, how do you handle extreme anomalies? Like a 100-core palace, which, for our global listeners, is a massive multi-million-dollar mega mansion just suddenly showing up in your neighborhood data.
Right.
Because that threatens to completely destroy your predictive model.
It absolutely will.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
It's fantastic to be here. And those three questions you just asked right at the top, those are the exact hurdles that separate a beginner, someone who just copies and pastes code from a true industry-ready AI engineer. Because so many people just jump straight into writing complex code, right?
Mm-hmm.
They import libraries, build neural networks without a second thought. But today, the goal of this deep dive is entirely different.
Yeah, we really want to completely remove the fear from the basic statistics used in machine learning.
Spot on. We need to introduce what I like to call the master question. It's the single most important question you have to ask before building any model, no matter how simple or advanced. And that question is simply, what does our data actually look like?
I'm really glad we're starting here because I know a lot of you listening right now, you probably have some Python experience. You know how to write a script. You've definitely imported a library or two like pandas or scikit-learn.
Yeah, everyone wants to jump to the fun stuff.
Right. You're eager to build the next big artificial intelligence tool. But the moment the word statistics gets dropped, it sounds like stepping back into a high school math class.
Oh, absolutely. It conjures up images of endless, terrifying formulas just written across a massive whiteboard.
But looking at what we're talking about today, it isn't about memorizing equations at all, is it? It seems much more behavioral.
It is entirely behavioral.
Mm.
And that's a huge misconception we need to break right now. Machine learning does not start with complex algorithms or massive mathematical formulas.
It really doesn't.
If you're starting there, you are already setting yourself up for failure. It begins purely with understanding variation. To give you a mental model, think of it as getting to know the personality of your data set before you ask it to do any work for you.
The personality of the data. I like that. It's like being a manager and inheriting a new team.
That's a brilliant analogy. Imagine you're a project manager and a new team of 50 people is assigned to you. You wouldn't just blindly hand out complex mission-critical tasks without first sitting down and understanding their strengths, right?
Right, their weaknesses, their quirks.
Exactly. How they behave under pressure.
Yeah.
You need to know if the team has highly uniform skills or if you have a chaotic mix of absolute beginners and seasoned veterans. Data is exactly the same. If you have 1,000 house prices, you need to know if they are all identical cookie-cutter suburban homes built in the exact same year, or if you're looking at an unpredictable mix of tiny studio apartments, run-down shacks, and sprawling celebrity estates.
So if I understand the approach here, the statistics are really just the vocabulary we use to describe that personality.
Exactly.
But let's ground this for the listener who just wants to write code. Why is spending time on this so critical? Like, let's talk about why skipping this getting to know you step is absolutely fatal for AI engineers.
It's the killer.
Because I've seen developers just import a library, toss their raw, unexamined data into a regression model, hit run, and just assume the computer will figure it out.
And that assumption is exactly why so many real-world AI projects fail spectacularly in production. The foundation of model behavior is completely inextricably tied to variation. If you do not understand the variation in your data, you cannot possibly understand how your model is going to behave when it encounters the real world. It's akin to building a massive skyscraper on quicksand without doing a soil test. Skipping this step impacts absolutely everything downstream in your engineering pipeline.
When you say everything downstream, what are we talking about specifically? Because, I mean, the code usually still compiles, right? It's not like Python throws a syntax error because you didn't check the variation.
No, and that is the most dangerous part. It is a silent failure. Your code will run perfectly. The terminal will show a nice little progress bar. It'll finish, and it'll give you a result. But your model will learn completely the wrong lessons from the world.
Wow.
We're talking about how you scale your features, which we'll dig into shortly. We're talking about the stability of your model during the training phase. And most importantly, we are talking about the magnitude of your loss functions.
Let's pause on that term, loss functions, because that's a big one for anyone transitioning into ML. In simple terms, a loss function is essentially how the model measures its own mistakes, right?
Correct.
It makes a guess on a house price, compares it to the real price, and the difference is the loss.
Precisely. The model updates its internal brain based on how big that loss is. If you haven't understood the variation in your data, say, you have wild, unpredictable swings in your house prices that you never bothered to investigate. Your model is going to make a guess, and the penalty it receives is going to be a massive, artificially inflated number.
I see.
That massive number gets fed back into the algorithm, and the model's internal weights experience a violent, unstable jump. It learns nothing useful because the feedback loop is chaotic.
So it's just thrashing around.
Exactly.
Yeah.
You will end up with a model that performs wonderfully on the specific flawed dataset on your computer, but completely implodes the second a real user types in a query.
Okay, that paints a terrifying but necessary picture. You really do have to do the groundwork. So let's dive deep into the actual shape of the data, starting with the very center of it all.
Let's do it.
If we go back to our core house price prediction scenario, our 1,000 houses, the first thing any human being naturally wants to know is the average. We call this the mean.
Yes, the mean. It is the balance point of your data.
Yeah.
If we want to use a physical analogy to really lock this in, imagine you have a giant, perfectly flat piece of wood, a seesaw.
Okay, a seesaw.
If you took all 1,000 of your house prices and placed them as physical weights along that piece of wood, cheaper houses on the left, expensive houses on the right, the mean is the exact precise mathematical point under that wood where you would place the fulcrum so that the board stays perfectly level.
So it doesn't tip left, doesn't tip right.
Exactly. In plain everyday language, it's the average value.
And when we look at the engineering side, the mean is an absolute workhorse. It shows up everywhere in the code base.
It is ubiquitous. In machine learning, the mean is constantly used for normalization, getting all your wildly different data points onto a similar playing field. It's heavily used for something called imputation.
Let's explore imputation for a second, because this is a daily reality for an engineer. Imputation is really just a fancy word for filling in missing data.
That's all it is?
Because real-world data is incredibly messy. If you're tracking house prices, maybe the database crashed for a week and you have 50 houses with no price listed. Or if you're working with IoT devices, maybe sensor number 4 loses its Wi-Fi connection for an hour, leaving blank spots in your dataset.
Yeah, it happens all the time.
And the algorithm cannot handle a blank space. It needs a number.
Exactly. An algorithm will just crash if you feed it a null value.
Yeah.
So a very common baseline strategy in the industry is to simply fill those blanks with the mean value of that specific column.
Right.
If the average house price in the neighborhood is 50 lakh and you have 3 missing records, you just type 50 lakh into those empty slots. It's a way of saying, I don't know the exact value, so I'll guess the most typical balanced value to keep the math running.
It's also used heavily for building baseline models, right? Like a sanity check for your complex neural networks.
That is a crucial engineering practice. Before you spend a week training a complex deep learning model, you should always build a dummy model.
Right, a model with no actual intelligence.
Yeah, a model that possesses zero intelligence and simply guesses the mean value for every single prediction. If your incredibly complex, highly tuned neural network cannot beat the accuracy of a model that just blindly guesses the average every single time,
then you know your complex model is fundamentally broken.
exactly, you've done something terribly wrong.
But looking at the deep dive materials here, there is a massive catch to the mean. And this is where your balance point analogy really shines and reveals its flaw. The mean is incredibly sensitive to extreme values.
It is dangerously sensitive. Let's go back to our physical seesaw. Imagine you have a perfectly balanced board. You've got hundreds of middle-class homes sitting nicely in the center. The board is hovering perfectly flat.
Okay.
Suddenly, someone drops a massive, sprawling billionaire's mansion on the far, far right side of that seesaw. What has to happen to the fulcrum, the balance point, to keep the board from violently crashing down on the right side?
You'd have to slide that fulcrum way over to the right to compensate for that massive weight.
Exactly. The balance point has to shift wildly to the right.
Yeah.
Mathematically, the mean gets dragged toward the extreme outlier, and suddenly that average number doesn't actually represent the typical middle-class house anymore.
It represents a distorted reality.
Precisely.
Which naturally leads to the next tool in our statistical toolbox. If the mean can be so easily skewed by one heavy weight, what's our alternative? This is where the median steps in. The median is, quite simply, the middle house.
I vastly prefer the median when dealing with real-world, human-generated data like housing or income. The median ignores the weights. It completely ignores the seesaw.
I love the mental image for finding the median. You don't use a seesaw. You literally just line up all the houses in a physical row.
Yep.
You start from the cheapest, most rundown little flat on the far left, all the way to the most expensive mega mansion on the far right, and you simply walk down the line, counting one by one, until you point to the house sitting exactly in the middle of the line. Plain and simple. It's the middle value based on position, not weight.
And why this matters in an industry setting cannot be overstated. The median is incredibly robust to outliers. Let's run that same billionaire scenario.
Okay.
You have your line of houses. You found the house in the exact physical middle. Now, what if that most expensive house on the far right suddenly gets renovated and triples in price?
Well, on the seesaw, the mean would fly off to the right.
But the median doesn't move a single inch.
Right, because the house in the exact physical middle of the line is still the exact same house.
It doesn't care that the last house in the line got more expensive. Its position hasn't changed. So when we translate this to algorithm behavior, the median is used heavily when you know your data is skewed.
When you know you have crazy, extreme values in your data set that would otherwise destroy a traditional average.
Exactly.
Okay, so the mean is the balance point. The median is the physical middle. That thoroughly covers the center of our data's personality. But knowing the center is only half the battle, that brings us to the next massive concept, variance. We know where the middle is, but how spread out are all these data points?
It is never enough to just know the center. You absolutely must know the chaos surrounding that center. Going back to our housing analogy, are all the houses in this neighborhood priced very similarly? Are they all within a few $1,000s of each other?
If so, you have low variance.
Right. The data points are tightly clustered, hugging closely to the mean. It's a very predictable neighborhood. But what if this neighborhood is a chaotic, unpredictable mix? What if you have tiny rundown flats sitting right next door to massive, sprawling luxury villas?
That would be a nightmare to predict. And that represents high variance.
Exactly. High variance means the data points are scattered far and wide away from the center. Now, why does an AI engineer need to care if the variance is high or low? Because variance directly dictates how the machine perceives importance, and it dictates model stability.
Let's break that down, because this is where the theory really hits the code. How does variance tear a learning algorithm apart?
Think about the loss function we discussed earlier. The way an algorithm penalizes itself. If you have incredibly high variance in your data set, it means the actual prices are wildly far away from the average. When your model makes a prediction, the errors it makes are going to be massive numbers.
Right.
And because of the way algorithms like gradient descent work, they take those massive error numbers and use them to take a step toward a better answer. If the error is huge, the step is huge.
So the model starts overcorrecting.
It overcorrects violently. It bounces all over the mathematical landscape. It guesses too high, gets a massive penalty, panics, guesses way too low, gets another massive penalty. It is literally thrashing.
Wow.
High variance without proper scaling can prevent a neural network from ever settling on a good answer. It just oscillates forever.
Which naturally leads us to standard deviation. And I think this is where people who aren't huge fans of math, the folks who just want to write Python, tend to glaze over. They see a Greek letter sigma and they just check out.
Oh yeah, panic sets in.
But standard deviation is actually a beautifully simple rescue operation for a mathematical quirk of variance.
That is a great way to frame it. Variance is a fantastic concept, but mathematically, to calculate variance, we have to square the distances between the data points and the mean.
Right, to get rid of negative numbers.
Exactly, so everything is positive. But doing that creates a massive problem for human interpretation. Variance is the squared spread. It's in a weird abstract unit.
Right. If you're calculating the variance of house prices, your unit is suddenly squared rupees or squared dollars, which means absolutely nothing to a real estate agent or a data scientist. You can't spend a squared dollar.
Exactly. It's conceptually useless for human intuition. Standard deviation comes in to save the day by simply taking the square root of the variance.
So it's consquaring it.
Yep. It takes that abstract squared number and brings it back down to the original unit, like rupees or dollars, so human beings can actually understand and visualize it. Standard deviation is simply the typical distance from the mean.
Let's give a really concrete example of that so it sticks.
Sure. Let's say our mean house price is 50 lakh rupees, which is roughly 60,000 US dollars. If we run the code to calculate the standard deviation and it comes out to 5 lakh rupees, or roughly $6,000, that single number gives us an incredibly clear picture of the neighborhood.
It tells us that the vast majority of houses lie perfectly within that plus or minus 5 lakh window.
Exactly. It tells us most houses will be between 45 lakh and 55 lakh. It visually defines the boundary of normal.
Okay, let's look at how this is applied in the engineering pipeline. Standard deviation isn't just a fun fact to put on a dashboard, it's a critical active tool. We use it for feature scaling. We use it for something called z-score normalization.
Yes.
I'd love to pause on z-scores because that sounds like heavy jargon, but it's incredibly practical.
A z-score is simply a way of asking the data, how weird are you? Instead of looking at a house and saying, this house cost 80 lakh, you use the standard deviation to change the language. You ask, how many standard deviations away from the mean is this specific house?
Ah, so you convert currency into a distance metric.
Exactly.
Huh.
If the mean is 50 and the standard deviation is 5, a house that costs 60 lakh is exactly 2 standard deviations away from the mean. Its z-score is 2.
That makes total sense.
And this is our primary weapon for outlier detection. If you write a script that flags any house with a z-score greater than 3 or less than -3, you have instantly built an automated anomaly detection system.
So if a house comes in with a z-score of 6, you instantly know it's a massive, potentially system-breaking anomaly, regardless of what the actual currency value is.
Precisely. It abstracts away the unit entirely.
That is brilliant. Which perfectly transitions us into the next major concept. We spent a lot of time on the center and the spread. Now we need to talk about the overall shape.
The shape is vital.
When you plot all these data points on a graph, a distinct shape emerges. The most famous of these is the Gaussian distribution, which most people know as the normal distribution.
The classic bell-shaped curve. It is the shape of reality for so many things in nature and human behavior. In a Gaussian distribution, the vast majority of the values huddle closely near the center, right around the mean.
Right.
As you move further away from the center in either direction, the number of instances drops off smoothly and symmetrically, creating that elegant bell shape. You have very few extreme cases on either the high end or the low end.
But why do machine learning systems care so much about this bell curve? Why is it considered the holy grail of data shapes?
Because many algorithms mathematically assume that your data follows this roughly normal behavior. The brilliant minds who invented linear regression, logistic regression, and Gaussian naive Bayes decades ago, they built the underlying math on the assumption that the errors in the data are normally distributed.
So they expect symmetry.
Exactly. When we apply scaling techniques, we are often actively trying to force our messy real-world data into a Gaussian shape so that the algorithms can digest it properly. If your data isn't Gaussian and you use a model that strongly assumes it is, your predictions are going to be fundamentally flawed from the very first epoch.
But let's be real for a second. We're talking about practical, industry-ready application here. Reality is almost never perfectly symmetrical.
No, it rarely is.
And that brings us to skewness. This is what happens when data leans heavily to one side. House prices, the example we keep returning to, are actually a perfect example of this. They almost never form a perfect bell curve in the real world. They almost universally skew to the right.
What's truly fascinating here is the physical, real-world reality causing that mathematical shape. Think about a house price. There is a hard physical limit on how cheap a house can be. It cannot drop below 0. You can't have a house that costs negative $10,000.
Right, the seller isn't going to pay you to take it.
Exactly. So the left side of your graph hits a solid wall at 0. But there's absolutely no limit on how expensive a house can be.
Right, someone can always add another gold-plated swimming pool. Or a helipad.
Precisely. A tiny handful of ridiculously expensive mansions stretch the right side of the graph out to infinity. They pull the tail of the distribution upward and far to the right. This destroys the symmetry of the bell curve. The data piles up near the lower end and bleeds out slowly to the right.
Here's where the engineering challenge arises. You can't just leave the data looking like that, right? If your algorithm expects a neat bell curve and you feed it a data set that looks like a hockey stick, the algorithm is going to perform terribly.
You absolutely cannot leave it. Dealing with right-skewed data often requires what we call log transformations. And this isn't just a magic wand. We need to understand the mechanics of what a logarithm is actually doing to the data.
Let's do a mental deep dive on that. How does a logarithm actually fix a skewed graph?
Think of a logarithmic function as a mathematical compressor that is highly aggressive on big numbers, but very gentle on small numbers.
Okay.
If you take the log of 10, it's 1. If you take the log of 100, it's 2. If you take the log of 1,000, it's 3. Notice how the gap between the original numbers was massive from 10 to 1,000, but the gap between the log values is tiny, just 1, 2, 3.
Oh, I see. So it punishes the massive outliers.
Exactly. By applying a log transformation to your entire column of house prices, those massive multi-million-dollar extreme values on the far right get compressed violently,
Right.
pulling the long tail all the way back in. Meanwhile, the smaller, normal house prices near the center are barely shifted. The result is that your heavily skewed, stretched-out graph suddenly looks remarkably like a nice, symmetrical bell curve. It's an elegant mathematical trick to make your data digestible for algorithms that demand symmetry.
That is such a clear way to visualize it. A mathematical compressor.
Okay, you've mentioned outliers a few times now, and we've talked about how they stretch the distribution, but I think we need to dedicate some serious focused time to them because they are the ultimate saboteurs of data science.
They really are.
Let's look at outliers and the devastating effects they have on relationships. Let's go back to our core dataset. A 100-core palace, a $12 million estate, suddenly appears in your Excel file of normal $60,000 suburban homes.
This is the ultimate industry scenario. You have this massive data point sitting there, and the immediate question every junior engineer asks in a panic is, should we just delete it? Is it bad data? It's the billionaire analogy, right? I love this thought experiment. Imagine a quiet, modest little village where everyone works at the local factory and makes a very similar working-class income.
Oh.
One day, a tech billionaire decides to buy a vacation home there and officially changes their residency to the village. If an economist calculates the average wealth of that village the very next day, the average wealth has absolutely skyrocketed. Statistically speaking, everyone in the village is now a multimillionaire on paper.
But the physical, lived reality for the villagers hasn't changed one bit. They're still working the same jobs for the same pay. The statistic is a lie.
Exactly.
That is a brilliant and completely accurate way to visualize the danger. Now, let's map that billionaire, that one single outlier, to machine learning. Let's look at how it severely distorts an algorithm like linear regression. Linear regression is trying to draw a straight line of best fit through your cloud of data points. It wants the line to be as close to as many points as possible.
It's trying to find the general trend.
Right. But that one massive outlier point acts like a supermagnet because regression uses squared errors. The loss function we talked about earlier, the penalty for being far away from that billionaire outlier, is astronomically huge.
Right.
To avoid that massive penalty, the algorithm violently pulls the regression line away from the cluster of normal houses, tilting it sharply upward just to get closer to the outlier.
So the line abandons the 99% just to appease the 1%.
Perfectly said.
Yeah.
It wildly inflates your mean squared error, or MSE. The distance from the true trend to the outlier dominates the entire math equation. Ultimately, this outlier bakes a heavy bias right into the core of your model.
And what happens in production?
If you let that model go live, it will overprice every single normal house it sees because it thinks the neighborhood is much richer than it actually is.
So the lesson for the engineer is clear. You have to actively hunt for them using things like the z-score we discussed, and you have to make a conscious engineering decision on what to do with them, whether that means clipping them to a maximum value, applying a log transformation, or straight up deleting the row if it's a data entry error.
Exactly. Do not let the algorithm discover the outlier on its own. It will not handle it well.
Okay, another massive trap that touches engineers constantly, and this is a big one, is misunderstanding relationships in the data. We've talked about individual features, but models are all about how features interact. Let's talk about correlation versus causation. This is the classic spurious relationship trap.
Your model's entire job is to find relationships between variables. So you look at your housing data and you notice something completely obvious. As the square foot area of the house goes up, the price of the house goes up. That is a valid, strong correlation. The two variables are moving together in the same direction.
Right.
And importantly, in this specific case, there is a real physical causal link.
Building a bigger house requires more bricks, more labor, and more land. Increased area directly causes the increased price. The logic tracks perfectly.
But then we have the causation fallacy. And this is the trap every data scientist needs to have tattooed on their arm. Let's step away from houses for a second and look at a famous real-world case study. You look at data for a coastal city over the course of a year, and you notice an incredible, undeniable mathematical pattern. On days when ice cream sales go way up, the number of tragic drowning incidents at the local beach also goes way up.
Wow.
The two lines on the graph move in perfect synchronicity. If you blindly feed that data set to a machine learning algorithm, what does it learn?
The algorithm, possessing no common sense, looks at the math and confidently concludes that eating ice cream causes people to drown. It might recommend banning ice cream to save lives.
Which is, of course, completely absurd. Both of those things, the ice cream sales and the drownings, are simply caused by a third hidden variable that the model might not even have access to: summer weather. When the temperature hits 95 degrees, people naturally buy ice cream to cool down. When it hits 95 degrees, thousands of people flock to the beach to go swimming. And tragically, with more people swimming, you have more drowning incidents.
So the relationship between the ice cream and the drowning is entirely spurious. They are correlated, absolutely, but there is zero causation.
Exactly.
I love that example. Let me throw another one at you that I read about in a study on education algorithms. An algorithm was trying to predict the reading comprehension level of elementary school children. It found a massive, undeniable correlation. Children with larger shoe sizes had drastically higher reading test scores. So big feet equals smart kids.
Another perfect example of a hidden variable. The algorithm doesn't realize that children with bigger feet are simply older. An 8-year-old has bigger feet than a 5-year-old, and naturally, an 8-year-old has been taught how to read much better than a 5-year-old. The shoe size doesn't cause the reading ability. Age causes both.
So when we translate this to algorithm behavior, what is the danger here? Because the algorithm doesn't know about age or summer weather, it just sees numbers.
The danger is massive when it comes to feature selection. If an engineer just dumps hundreds of random features into a model and hits run, the algorithm will find correlations. It is mathematically designed to find patterns.
Uh-huh.
But if those correlations are spurious, if they're just random coincidences or driven by hidden variables, your model's going to make absurd, dangerous predictions in the real world.
You're basically building a model on a foundation of illusions.
Exactly.
Let's stick with this concept of relationships for a moment and look deeper into the mechanics of it. We know correlation says these things move together, but looking at the advanced concepts here, we have this idea called covariance. What is the distinction?
Covariance is the foundational mathematical building block. If correlation is a polished, normalized metric, covariance is the raw, unscaled engine underneath it. Covariance tells us about the direction of the relationship. It gives us a directional compass. If we run the math and see a positive covariance, it means as one variable goes up, the other variable goes up. House area increases, price increases.
And a negative covariance would just be the inverse. As the age of the building increases, as it gets older, the roof starts leaking, the plumbing gets rusty, the price decreases. One goes up, the other goes down.
Exactly. Now, the reason we don't often stop at covariance is that the actual number it spits out is very hard to interpret, much like variance. It depends entirely on the units.
Right.
If you measure the house in square feet versus square meters, the covariance number will wildly change, even though the physical relationship is exactly the same. That is why we usually standardize covariance into correlation, which always gives us a neat number between -1 and +1.
But understanding raw covariance is the absolute foundation for advanced techniques, specifically mentioning PCA or principal component analysis. Let's spend some real time here, because PCA is a technique that separates the juniors from the seniors. If covariance is just a directional compass, how does PCA use it?
This is one of my favorite concepts in all of data science. Let's visualize a 3D space. Imagine you have a data set with 3 features: number of bedrooms, square footage, and number of bathrooms. If you plotted every house as a dot in a 3D room, you would have a big cloud of dots hovering in the air.
Okay, a 3D cloud.
Now, PCA is a dimensionality reduction technique. Its entire goal is to take that 3D cloud and squash it down into a flat 2D piece of paper without losing the essential shape of the houses.
Why would we want to squash it?
Because algorithms struggle with too many dimensions. If you have 500 features, the math gets impossibly complex and the model overfits. It's called the curse of dimensionality. We want to reduce 500 features down to the 10 most important super features that capture the most variation.
There's that word again, variation.
Exactly. This all loops back. To squash the 3D cloud, PCA looks for the angles where the data varies the most. And how does it find those angles? It uses covariance. It builds a massive grid, a covariance matrix, that mathematically calculates exactly how the bedrooms interact with the square footage, how the bathrooms interact with the bedrooms, and so on.
So it's looking for the redundancies. It realizes that if a house has 5 bedrooms, it almost certainly has a huge square footage and multiple bathrooms.
Precisely. The covariance matrix exposes those tight relationships. PCA then uses some heavy linear algebra calculating eigenvectors to draw new lines right through the thickest, most spread out parts of the data cloud.
Ah.
It essentially says, I don't need bedrooms, bathrooms, and area. They're all basically telling me the same thing, the size of the house. So it creates one single new feature called Principal Component 1 that captures the variation of all three. It flattens the 3D cloud onto a 2D plane based entirely on the covariance relationships.
That is mind-blowing when you visualize it. It's taking a 3D taco shape of data and perfectly flattening it without losing the essence of the taco. And none of that is possible without understanding how the features vary and covary.
If you don't understand variance and covariance, PCA just looks like black magic.
Yeah.
But when you understand the foundation, it becomes an incredibly logical, elegant tool.
Okay, I want to take a slight pivot here. We are an AI and ML engineering channel, and our listeners are developers who spend their days in IDEs like VS Code or Jupyter Notebooks.
Sure.
So let's talk about the code logic explanation. We aren't going to sit here and read Python syntax character by character that makes for terrible audio, but we absolutely need to walk through the logic under the hood.
Let's do it.
Let's do a mental debugging session. Let's say I want to find that middle house the median and my senior developer has forbidden me from using any built-in magic functions from NumPy or Pandas. I have to write the logic from scratch. How does the code actually flow?
It is a surprisingly elegant coding exercise that really tests if you understand the concept. Remember our physical analogy? Lining a physical houses up on the street. The code logic must mimic that physical reality. First, and this is where beginners trip up, you absolutely do not use any summation loops. You don't add a single number together.
Right, because if you add them, you are inviting the billionaire outlier to ruin the math.
Exactly. Instead, you take your raw array of house prices and you apply a simple sorting algorithm. In Python, you might just call dot sort on the list. You organize the array from the smallest numerical value at index 0 to the largest numerical value at the end of the list.
So the computer has now built our physical street of houses in its memory, smallest to largest.
Step 1 is complete. Now step 2. You must programmatically find the exact center index. This requires some basic positional math. Let's say your array has an odd number of items, exactly 1001 houses. You take the length of the array, you divide it by 2 using integer division so you don't get a decimal, and that gives you index 500. You simply return array bracket 500. You just pull the value out of that slot.
But what if it's an even number? What if I only have 1,000 houses? There is no single middle house. The middle falls exactly between house 500 and house 501.
Good catch. If the length of the array is an even number, the logic branches. You have to programmatically grab the two middle indices, index 499 and index 500 in Python. Since we start at 0, you extract both of those values, add those two specific numbers together, and divide by 2. You take the mean of just the two middle houses.
That is so elegant. The core logic is purely positional. It is about sorting arrays and calculating indices, not accumulating massive sums. That is the programmatic reason why it ignores outliers entirely. The 100-core palace is just sitting harmlessly at index 999. The code never even looks at it.
Exactly. It completely isolates the extreme values based on position. Now let's look at another piece of code logic. Standardization. We talked about z-scores and getting things on the same scale using the mean and standard deviation to build anomaly detectors or prep data for neural networks. If I have to code a standardization function from scratch, what does that loop look like?
Let me take a swing at the logic for this one. It seems like a two-step mathematical process applied to every single data point individually. So I would write a for loop that iterates over every house price in my list.
Correct. You loop through the array.
Inside the loop, step 1, I take the specific house price I'm currently looking at, and I subtract the overall mean of the entire neighborhood from it.
And what does that mathematically achieve?
It centers the data. If the house is exactly the average price, subtracting the mean makes it 0. So now my average is officially 0. Some houses will be positive numbers, some will be negative numbers.
Spot on. The data is now centered around 0. What is step 2 inside the loop?
Step 2. I take that new centered number and I divide it by the overall standard deviation of the neighborhood. This rescales the feature. It squashes or stretches the data so that the variance is exactly 1.
You've got it perfectly. You loop through your entire data set, subtracting the mean and dividing by the standard deviation for every single entry. Suddenly, all your wild, vastly different numbers, prices in the millions, square footage in the thousands, age in the tens, are abstracted away.
That's amazing.
They are all speaking the exact same statistical language of z-scores. They are all centered at 0 with a spread of 1. Neural networks absolutely love data formatted this way. It allows the gradient descent engine to learn incredibly fast and stable.
Okay, understanding that code logic is empowering, but knowing when and why to apply it brings us to a massive section of our discussion: common engineering mistakes. What happens when developers ignore these foundational steps? We already touched on assuming correlation equals causation, which leads to those spurious relationships and ridiculous models that ban ice cream. But what about ignoring multicollinearity? You mentioned this briefly earlier when we talked about PCA, but let's really unpack it. What is it, and why is it a trap?
Multicollinearity is a massive, incredibly common mistake I see constantly in industry code bases, even from mid-level engineers. It happens when two or more features in your data set move together too strongly. They're highly correlated with each other, not just with the target variable. They're essentially telling the model the exact same piece of information, just in slightly different fonts.
Give me a real-world example of that.
Let's look at our housing data. Imagine you feed a regression model the area of a house measured in square feet as feature A. And then further down the spreadsheet, you have another column for the area of the house measured in square meters. You feed that in as feature B.
Well, obviously, those are perfectly correlated. One is just a mathematical constant multiplied by the other. They're the exact same thing.
To a human, yes, it's obvious. But the algorithm does not know what a foot or a meter is. It just sees two distinct columns of floating point numbers. It assumes they are two entirely different, independent pieces of evidence to help it guess the price.
So what happens inside the math engine when it tries to use both?
Total confusion. Think of it like a commercial airplane with two co-pilots who are both trying to steer the plane based on the exact same instrument reading. When the algorithm tries to assign an importance weight to the square footage, it looks at square meters and gets confused. It says, wait, should I give all the credit for the price increase to feature A or feature B?
Because they both perfectly predict the price change.
Yep. Exactly. The mathematical weights inside the algorithm destabilize. The matrix math actually is what we call a singular matrix, which is a fancy way of saying it's on the verge of dividing by 0.
Oh, wow.
The model might arbitrarily assign massive positive importance to square feet and massive negative importance to square meters just so they cancel each other out. It completely ruins the interpretability of your model. If your boss asks you which feature is most important, your model will give you garbage answers because it's tearing itself apart trying to balance two identical features.
That is a terrifying thought. You think you are giving the model more data to be smarter, but you are actually just giving it multiple steering wheels and causing it to crash. And the other massive engineering mistake, which we covered but needs reinforcing, is failing to remove or treat outliers. As we explored with the billionaire analogy, it severely distorts the regression slope, it massively inflates the MSE loss, and it bakes a heavy, unshakable bias right into the core of your model.
I want to tie all these mistakes together. Whether it's spurious correlations, multicollinearity, or outlier distortion, they all stem from the exact same root cause.
Failing to answer the masking question.
Precisely. Failing to ask, what does our data actually look like before writing the predictive algorithms? If you just load a CSV file into scikit-learn without visualizing it, checking the variance, or running a correlation matrix, you are flying blind into a storm.
Which brings us perfectly to the applied integration with our ongoing project. For everyone who has been following along with the house price prediction project on the channel, this is how you bridge all this theory into reality. Before you write a single line of predictive logic, before you import a random forest, a support vector machine, or a neural network, you as an AI engineer must explicitly map out the personality of your housing data.
You must write the scripts to calculate and visualize the mean and the median to understand your center and see if they differ wildly. If the mean is way higher than the median, you instantly know you have right-skewed data. You must calculate the variance and standard deviation to understand your spread, and use that standard deviation to hunt for anomalies.
Right.
You must plot the distribution as a histogram to visually see the shape. Is it a beautiful bell curve, or does it skew hard against the zero wall? And you must run a correlation matrix, a heat map, to ensure you aren't feeding the model redundant multicollinear features or falling into causation traps.
If you do that groundwork, you ensure the model doesn't learn the wrong patterns. You ensure it is learning the actual reality of the real estate market, not just a mathematical hallucination caused by dirty data. Okay, to really cement this for our listeners who are preparing for job interviews or heading into sprint planning meetings, let's do an engineering checklist. Let's do a role play scenario.
Sounds fun.
I'm going to play the role of a stressed senior engineer in a sprint review throwing industry jargon at you, and you are going to translate it into plain, intuitive English for the listener. Are you ready?
I love this exercise.
Yeah.
I am ready. Let's do it.
All right. We are in a tense sprint review meeting. I pull up the analytics dashboard, point at a specific column in our database, and I say, this feature is completely unusable right now. It has massive variance.
Translation. The numbers for that specific column are wildly unpredictable. They're scattered far and wide away from the average. It is a chaotic mix of tiny numbers and huge numbers, not a tight, predictable cluster. We need to figure out why it's so chaotic.
Okay, I swipe to the next slide. I point to a histogram graph and say, look at this. The distribution is heavily, heavily skewed.
Translation. The data leans far more to one side instead of sitting nicely in the middle like a bell curve. Usually this means there's a hard limit on one side like 0, and a few extreme outliers are stretching the tail of the data far out to the right. We probably need to apply a log transformation to compress it.
I nod in agreement, and then I ask the junior dev, before you fed this into the neural network, have we standardized the feature?
Translation. Have we run that two-step loop? Have we rescaled every single data point by subtracting the mean to center it at 0 and dividing by the standard deviation to give it a uniform spread? If not, the neural network's gradient descent is going to choke on the raw numbers.
Finally, I look at the correlation heat map. I sigh and I say, we can't run the model like this. We have massive multiclinearity in this data set.
Translation. 2 or more of our columns are essentially identical twins. They're moving together way too strongly, and if we leave them both in, they're going to confuse the math engine like two pilots fighting over the controls. We need to drop one of them or use PCA to merge them together.
Perfect. That translation drill is absolute gold for anyone trying to break into the industry. If you are listening to this, rewind and listen to that drill again. That is exactly how you sound like an industry professional in a stand-up meeting. You don't just use the words, you understand the mechanical reality behind them. So, what does this all mean in summary? Let's do a rapid synthesis of the core pillars we've established today.
We have established the 4 absolute core pillars of data variation. The mean and median represent the center of your data's universe. The variance and standard deviation represent the spread and chaos around that center. The distribution, whether Gaussian or skewed, represents the overall shape of reality you are dealing with. And covariance and correlation represent the hidden relationships acting within the data.
And the final reminder, the big takeaway from this entire conversation, machine learning does not start with algorithms. Algorithms are just engines. The process starts entirely with understanding data variation.
I will say it again because it is the most important sentence of the day. If you do not understand the variation of your data, you absolutely cannot understand or predict the behavior of your model. It is that simple.
Okay, here's where we put you, the listener, to work. We don't just want you passively listening, we want you building muscle memory. We have a highly practical exercise for you, and I strongly encourage you to do this immediately after listening. It'll take you maybe 5 to 15 minutes tops. Open up your Python terminal or launch a fresh Jupyter notebook. I want you to create a very simple Python list of 10 typical house prices. Let's say 10 values hovering right around 50 lakh, maybe 1 is 48, 1 is 52. Keep them tight.
Now write the simple logic to calculate the mean and the median of that specific list. You can write the loops from scratch to test yourself or use NumPy's built-in functions, whichever you prefer.
Now here is the crucial eye-opening part of the exercise. Inject a massive outlier into your list. Add an 11th house to the array and make it that 100 crore palace. Make it 10,000 lakh. Make it a ridiculously huge number compared to the other 10.
Then simply recalculate both metrics. Run the exact same mean and median code again.
Watch exactly what happens in your terminal output. You'll see the mean wildly explode. That balance point, that seesaw, will be completely destroyed by the billionaire house. But look at the median output. You will observe that the median remains perfectly, stubbornly stable. It might shift by one single index, but the value will barely change. Doing this with your own hands and watching the output change on your screen intuitively proves why the median is robust to outliers. It takes the theory out of your ears and hard codes it into your brain.
And this exercise sets the absolute perfect foundation for what is coming next in our curriculum. Today, we dedicated our entire time to understanding how data varies. We stayed entirely in the realm of describing the data we currently have in our hands. But in our next deep dive, we are taking a massive leap forward. The next lesson is how data infers.
Oh, that is going to be a brilliant transition. We are going to move away from just describing a static historical data set, and we're going to start doing the real magic of data science, drawing conclusions about the future from limited samples.
That is precisely where true statistical confidence begins. How do we know if the patterns our model found are actually real universal truths, or just a random fluke of the specific sample we downloaded? How do we know we aren't being fooled by randomness? That is the power of inference.
I cannot wait to unpack that. Now, a mandatory call to action for everyone listening. Go try that Python exercise right now. Seriously, pause the audio, open your terminal, and build the list. Once you've done it, write your observations or any questions you have in the comments section below the video. Did your mean explode as expected? Did you try writing the median logic from scratch? We read the comments, and we want to see your aha moments. Remember to like this video, share it with your fellow developers who might be struggling with these foundational math concepts, and subscribe to the channel so you do not miss the next critical lesson on inference.
And as a final, provocative thought for you to mull over as you close your notebook, we have spent the last hour talking about outliers as villains. We talked about finding them, clipping them, deleting them, and using medians to hide from them, all to protect our regression models.
Yeah.
But I want you to ask yourself, what if you were building an anomaly detection system for a bank to catch credit card fraud, or a medical AI looking for rare tumors? In those specific scenarios, the normal data is the boring noise you want to ignore. The massive outliers are the only things you actually care about. How does that completely flip the mental model of statistics we just built today?
Boom, let that sink in. The anomaly becomes the target. We will leave you with that fascinating paradox. Keep coding, keep questioning your data's personality, and we will see you on the next deep dive.